Okay, guys, sorry, there is a problem having with my computer and it starts. Okay, can you hear me now? Sorry for this problem, technical problem from my computer. Sorry again. Okay, now we go back to our slide again here. So we have the force equal to K times delta, with delta equal to U2 minus U1. This is equation number one. So U2 is the displacement at point 2 minus the displacement at U1. So this is the total displacement of the element will be U2 minus U1. Okay, so if we consider the equilibrium of forces for the spring at node 1, we have F2 equal to F1, sorry, equal to negative F, which is negative K times U2 minus U1 equal to KU1 minus KU2. This is equation number 2. And at node 2, we will have F2 equal to F, which is K times delta or K times U2 minus U1 will equal to minus KU1 plus KU2. So if we write these two equations in a matrix form, we will have K minus K minus K, K times U1, U2 will be equal to F1, F2. And this gives us that Ku equal to F, where K is the matrix of the spring, which is K minus K minus K and K. U is the displacement or element nodal forces, nodal displacement, which is U1 and U2, and F is the element nodal forces, F1 and F2. Okay? Do you understand this explanation of the spring? I can explain with you again if you want. I will just share my just quickly to understand what is here. So if we have the spring here, we have node 1, node 2, and U1, U2, and the stiffness K, and we have F1 and F2. Okay, so what we know that F, general rule, F equal to K times delta. K is the force, sorry, F is the force, K is the stiffness matrix we are looking for, delta is the displacement. Here we know that F is F1 and F2. We don't know K. Delta is U1 and U2. Okay. The value of delta, if you have, this is our direction X. So delta, the total displacement of the member, the whole will be U2 minus U1. So we get a relation between U1 and U2 and delta. Okay. For the force, from this equation, we have F1 will be K times delta. Delta is U2 minus U1. Okay, but the force here, F1, go to the left. So that's why we will give it a symbol, oh sorry, a negative sign. Okay, so the negative sign because the force F1 is going to the left. Okay, so for F2, we have F2 is going to the right, so it will be positive, and the force is K times U2 minus U1. So here, because we have F2 in this direction. Okay, so we have these two equations now. If we write them in a matrix form, we will have F1 and F2, this is the forces, equal to, first of all, just make it more simple here. I will try to make it simple here. So now you know that negative means to the left, positive means to the right. So F1 here will be K U1 minus K U2. I'm trying just to get U1 first and U2 second. For this one, F2 will be minus K U1 plus K U2. So we have F1 and F2, U1, U2, U1, U2. So if we return back to our equation here, we will have U1 and U2. And here we will have K minus K minus K and positive K. So this is the force. This is the stiffness matrix. And this is the displacement. Okay. So now you know how we derive the stiffness matrix of a spring, which is K minus K minus K positive K. Okay. Do you have any question or for this one? So this is how we can derive the stiffness matrix. What you need to know is the stiffness matrix of a spring will be something like that: K minus K minus K K, where K is the value of the resistance of the spring. Now we return back to our slides. And the second element we need to know is the bar element. If we have a bar element like this, if we have a bar element, or consider a uniform prismatic bar element, we have L length of the element, and the element has two nodes, 1, 2, end and like beginning and end. We have area, and E is the Young modulus. So this is the properties we have: length, cross-section area A, and E is the Young modulus E. So we have applied force F11 here at node 1 and F21 at node 2, and the direction of or the displacement we have is U1. So here for bar element, we have two nodes. So we have like what we call like the consequence of the deformation of U1 on force F1, and we have the consequence of deformation U2 and F2 and F1. So we have U1 will cause F11 and F21, and we have U2 cause F12 and F22. To understand this, we have, for the force, we have two numbers, F1, 1. So I is the first number, is the number of nodes. I, the second one, is the effect of deformation at node 1. So F11 means the force at node 1 as a consequence of displacement U1, or as a result of U1. F21 means the force at node 2 as a result of displacement at U1. That's why this is the case of U1 here on the top. The second case, or case B, same element, we have F12 and F22 due to FU2. So as you can see here, U2 will cause F12. So F1 means force at node 1 due to deformation at node 2. F22 means the force at node 2 due to the deformation at U2. Okay? from the stability of this element, F11 should be equal to F21, because if we push U1, so the force F11 equal to F21. And also when we pull U2 like that, so F12 equal to F22. So we have two conditions here, that F11 equal to F21, F12 equal to F22. Another notice here, if you can see why the force F11, F21 is going inside the element or compress the element, and why F12, F22 are inside or pulling the element. Because here, as you can see, U1 is pushing to the right because this is a positive direction. So F11 and F21 will causing compression. That's why the force are going into the element or compressing the element. For U2, it is like also U2 in this direction because this is a positive direction, and U2 is bullying, causing a bullying force F12 and F22. Okay, so this is the conditions we have to find the force. So how many forces we have for this element? Four forces, F11, F21, F12, F22, because we have two nodes. So each node, the deformation or the displacement at each node will cause force at each node. So we have four forces or four components. The component will be, if to get the components, we will assume that the displacement in the bar is delta. Then we have delta equal to FL divided by AE. This is the equation where F will be AE divided by L times delta. Okay. So the displacement or the elongation, this is the elongation in member, the bar element, delta equal to the force times L divided by EA. Okay. This is how to get the deformation or the elongation in bar element. So to get the force in one side, so F will be delta times AE divided by L. So this is the general force for the bar element, F equal to EA or AE divided by L times delta, where delta small is the displacement in the bar element. Okay. For the respective cases in the above figure, so if we return back to the above figure, so now we can get F11 and F21. So F11 and F21 will equal to AE divided by L times U1. Why U1? Because U1 causing F1, F21. So again, F11 means force at node 1 due to U1. F21 is the force at node 2 due to U1. So F11 and F21 will equal to the general rule for displacement or forces, but using U1 here. And F12 similarly will be F12 means F1, the force at node 1 due to displacement at node 2, and F22 force at node 2 due to displacement at node 2. So it will be same, but instead of U1, it will be U2. So again here, the forces are associated with displacement node 1 and 2. Okay, so if we write it in a matrix form, so we will have F11 and minus F12 minus F21, F22 times 1 by 1 equal to F1 and F2. So the first F1 and F2 are, we get the component of them, F11, F12, F21, F22. Or we can write it in the displacement form, AE divided by L times 1, negative 1, negative 1, 1, U1, U2 will equal to F1 and F2. Okay, so as you can see here, the equation to the right is the general or the matrix equation of the truss. From this equation, we can get the matrix, the element matrix of a truss element. Okay, because, as you know, the force equal to K times delta. So this is delta, this is the force. So the first part, AE divided by L times 1, negative 1, negative 1, 1 is the stiffness matrix. Okay, so this is equation number 10. If you see at the bottom of the slide, K for a truss element is EA divided by L times 1, negative 1, negative 1, 1, because this part, AE by L, is a scalar or a constant, so we can take it as a common factor and get it out of the element of the matrix. Another way to write it is EA divided by L, negative EA by L, negative EA by L, and EA by L. Okay, so from this slide we can notice that the stiffness matrix of a truss element is 2 by 2 element, and the values of this 2 by 2 element is 1, negative 1, negative 1, 1 times EA by L. And this is how to derive it. We don't need to know or keep in mind how we derive it, just for your information. No question, I think, will be for how to derive the stiffness matrix. But now you know how to do it. So if you need to go through it again, you can go through it and let me know if you have any questions. Okay. So this part is how we get the stiffness matrix for like a spring element and bar element. Both of them are quite similar procedure. This method to get the matrix is the direct method. So this is our first method to get the matrix. There is another method, but a little bit complicated. So we will do it after rest. So maybe we take a rest for 10 minutes and we meet again in like 12:15 in Adelaide time. So see you after 10 minutes. Okay, guys, I'm back. So again, the last part of our session was like how to derive the stiffness matrix for a truss using the direct method. And finally, we get the stiffness matrix of a truss element as K equal to AE by L times 1, negative 1, negative 1, 1. So for a truss element, the stiffness matrix is 2 by 2 elements. And this are the values of the stiffness matrix or the parameter of the stiffness matrix of a truss. So now we get into the second step, the second method to get the finite get the stiffness matrix for any element. It's a little bit complicated, so we will go through it like briefly. We don't need to go in details with this one. You can go through it if you want and discuss with me later. But at the end, we will get the same result we get from the direct method, but this is like a formal procedure to get the stiffness matrix for any complicated or any uncommon element. Okay, but for common elements, we'll give us same value, so we don't need it too much in our course, but just to know it. So the formal procedure is to derive the same matrix as we get for the bar, but using a formal procedure that can be applied to any other complicated situation. Okay. For different type of element, the variation of the displacement between the nodes must be assumed first. So to get in this formal procedure, we need to know what is the behavior of the element. If it is expanding, compressed, there is deflection, rotation, and torsional, something like this. So we need to know exactly what is the behavior or expect the behavior of the element that to assume the unknown parameter we need. So this is called the displacement function. So the displacement function is what we will assume to find the stiffness matrix of any element or any complicated element. This displacement function is usually a polynomial whose order depends on the number of degree of freedom in element. So in each element, according to the behavior of the element or according to the element type, we expect number of degree of freedom. Number of degree of freedom is the expected displacement or rotation at each node. So if it's like truss element, we expect one one degree of freedom at each node. If it is beam element, we expect 2 degree of freedom. If it is a 3D element, we expect 6 degree of freedom at each node. So depending on the type of element and the behavior of element, we assume or we expect the degree of freedom. Okay. So degree of freedom means the number of components of the displacement vector at each node. And this is variable depending on the element type. Okay. So now we start the formal procedural method for a bar element. For bar elements, they are used to model trusses or truss structures. And as you know, any truss can carry only axial load, which is tension or compression forces. Okay. So in trusses, we know that the axial effect is predominant, and the bar element consists of 2 degrees of freedom per element. And this is again, as I mentioned before, each node of a truss element has 1 degree of freedom. So the element has 2 degrees of freedom because it has 2 nodes. Okay, so the displacement function for a bar element can be written as u equal to beta 1 plus beta 2 times x. So beta 1 and beta 2 are the polynomial function parameters. X is a variable, x is a distance, so x is our variable. So the displacement u is a function in x. And this is formula 11 is called as we mentioned in the last part, is the displacement function. So this is the displacement function for a bar element. Okay. So the finite element modeling treats the nodal displacement as variable of an interpolation function, usually a polynomial, to give an analytical expression for the displacement at any point inside the element. So using this function or displacement function, you can find the displacement at any node on the element, not only the end and start nodes. So for this method, it's using the interpolation to get the displacement at any node. So this is the general equation we will use to get the stiffness matrix, and we call it a displacement function. So to find the displacement function values, beta 1 and beta 2, we are using this expression. So if we write equation 1 in by expressing beta in terms of displacement u1 and u2, so at x equal to 0, the displacement is equal to u1, which is beta 1. At x equal to L, u is equal to u2, which will be beta 1 plus beta 2 times L. These values get from just here. If we substitute x using 0, so this term will be omitted. If we substitute at L, so x will be L, so it will be B to L. So that's from where we get these two values. And if we replace beta 1 and beta 2 into equation 11, so we will have u equal to 1 minus x by L u1 plus x divided by L u2. Okay? Can you understand this from where we get this equation? Just using these two equations on the top, so we get a value of beta 1 in times of u1 and get value of beta 2 in times of u2. So the final equation of u will be 1 minus x divided by L times u plus x divided by L times u2. If we want to define these two linear shape function as follow, so the first parameter is 1 minus xl. This is beta 1 or n1. We call it now n1 instead of beta 1. So beta 1 equal to n1 as a function of zeta will be 1 minus zeta, where zeta equal to x by L. So n2 will be zeta. So what we have done is just to replace x divided by L with a symbol zeta. So zeta is x divided by L, where zeta from 0 to 1, because the maximum value of x is 0, so zeta will be 0. The minimum value of x is 0, so zeta will be 0. The maximum value of x is L, so zeta will be 1. Okay? So this is the shape function of a bar element, 1 minus zeta and zeta. Okay? Each shape function n I describe how u varies with x when the corresponding degree of freedom u1 is unity while the other is 0. Okay? So the shape function describes the value of x of u, or how the value of u, the displacement, varies when x is corresponding to u. So if we are at u1, so x will be 0. If we are at u2, x will be equal to L. So we just take in consideration one u and the other is 0. So u will be L minus x divided by L and x by L. Okay, so from here, what we have done is just instead of 1 minus x by L, we take the L as common and we will become L minus x divided by L. So what we have here is L minus x divided by L and x divided by L, or we can write it in a matrix form, a general form, u equal to n times d, where n is the shape function matrix consisted of n1 and n2, and d is the vector of element degree of freedom. Okay, so how many degree of freedom we have? 2, u1 and u2, and the shape function is L minus x divided by L and x by L. As you can notice, the n shape function or the shape function is a row vector, because u should be a value of a scalar, so it is only one value, so it should be a line vector times a column vector. So a row vector times a column vector will give us only one value. Okay, and this is the shape of the shape function represented here by n1 and n2. So as you can see, the shape function n1, where u1 is 1 and u2 is 0, so n1 will be L minus x divided by L. The other shape function at node 2, so the u2 will be taken as 1, so the shape function n2 will be x divided by L. Okay? In between, so if we have u1 and u2, using the polynomial, using the interpolation equation or interpolation function, U will be N1 U1 plus N2 U2. So the displacement at any node on the element will be as this one, N1 U1 plus N2 U2. But the displacement at or the shift function at one when one U1 is 1 and U2 is 0, this is the value of it. Shift function N2 while U2 equal to 1 and U1 equal to 0 will be N2 equal to X by L. So this is the shift function and the interpolation. Then, so this is our shift function. And then the second step after this is the axial strain. If we need to get the axial strain from this shift function, so the strain will be the derivation of u according to x, so du by dx. So this means that we will get the derivation of the shape function n and times d give us b times d. So the strain, this is the final formula we need to know. The strain in a bar element equal to b times d, where b is the element strain displacement matrix and d is the displacement matrix. D will equal to negative 1 by L, 1 by L. Where does this come from? B. If we return back to N, where is N? This is N. So N, if we derivate N according to X, this will be negative 1 by L. If we derivate XL according to X, it will be 1 by L. So this shift function, this element strain displacement matrix B is negative 1 by L, 1 by L. And if we have the strain ready, so we can get the stress. So the stress is equal to E by strain, E by epsilon. So E is the Young modulus or elastic modulus, epsilon is the strain. If we substitute strain from equation 15, so strain equal to B times D. So to get the stress directly in a bar element, we have E times B times D. So where E is the scalar of elastic modulus, B is the strain displacement matrix, D is the displacement matrix. Okay. And this is strain energy stored in a bar. We can have a look on this equation. It is a bit complicated. So U is the strain energy equal to half D transpose times integration B transpose E B according to V. All of this times D displacement matrix. The work done by the nodal forces is W equal to 0.5 F1U1 plus 0.5 F2U2 or equal to 0.5 D transpose F. For conservative system, the strain energy should be equal to the work done. Otherwise, the system will be unstable. So if we equate these two equations together, we will find that 0.5 D transpose integration B transpose EB according to V will times D will be equal to 0.5 D transpose F. So at the end, we will find that KD equal to F. Okay. So this is the general result we get from the direct method, that at the end, the stiffness matrix K times the displacement vector D will equal to the forces. Okay. And using equation 24 and to calculate the stiffness matrix of the bar element, so it will be integration of 0L from 0 to L B transpose times E times B times A dx will equal to AE divided by L 1, negative 1, negative 1, 1. So what we need to know that even the function, the shift function will give us similar result to the direct method. So as you remember from the maybe 20 minutes, we get the stiffness matrix for a truss or a bar element as AE divided by L times 1, negative 1, negative 1, 1. So we get the same values of the direct method. Okay. In a general form, we can write the strain energy as 0.5 d transpose kd. I know it is a bit complicated, the shift function, but this method can be used for any complicated. This is a general or formal procedure to get the stiffness matrix for any member. Okay, but it will give us the same result as direct method, so we can just recognize the value of the stiffness matrix. Okay, this is an example of the truss element. We need to find the stresses in a two-bar assembly, which is loaded by a force B and concentrated at the two ends, as shown in figure. Okay, this will be an example we will solve together today, but I will leave it to the last part of the session. So to apply on the bar element. Okay, so this example will be done later today. So we'll just delay it for a bit. And now we get into the beam element. So the beam element, we need to also use the shape function n to find the model, the nodal displacement of the beam element. Okay, so the shape function here will be a little bit complicated, more than the bar element, because we have more degree of freedom at each node. As you can see here, the beam element is used to model beams or frames with flexure effect. As you know, the flexure effect, including the shear forces and the bending moment. So for this type of element, we have two types. Beam elements, which just including the flexure effect, shear force and bending moment. And we have frame element, which including the flexure effects and axial effect. So axial effect means that we have also another force applying to the frame element, which is the axial loads. So one of them will only include the flexure effects, and the other will include the flexure and axial effect. Okay, so the beam elements, which is only containing the flexure effects, will only contain 4 degree of freedom per element. Okay, so 4 degree of freedom, as you can see, what is the degree of freedom for a beam element? This is a general beam element here at the bottom of the slide. So we have a beam element. The start is node I, the end is node J. X is this direction, Y is this direction. The length of the member is L. Here, because we are including the flexure effect, so we have E and I. What is E? E is the Young modulus or elastic modulus of the material. I is the inertia. Because as you know, the inertia of a member resists the flexure effect. The area resists the axial effect. So because this only member under flexure effect, so we need E and I. The degree of freedom, as you can see, is in black here. What is the degree of freedom we have? We have vertical displacement VI. We have rotation theta I. At J, we have Vj and theta J. So the degree of freedom at each node of a beam element are 2. Vertical displacement and rotation. Why we have vertical displacement and rotation? Because at each node we have nodal forces, 2 nodal forces. Fi, which is representing shear force, and Mi, which is representing the moment. And also at node J, we have 2 nodal forces, Fj, sorry, which is shear force at J, and Mj, which is the moment at J. So how many degree of freedom we have for a beam element? 4 degree of freedom. So what is the size of the stiffness matrix for a beam element? Can you expect the size of a beam element? I will give you a hint. The size of a beam element is the number of degree of freedom times the number of degree of freedom for the whole element. So the number of degree of freedom is 4. So the matrix will be 4 by 4. Okay. And the shape function will be including 4 parameters of polynomial, and the order will be on 3 order. So the polynomial will have a level 3 order. So V is the shape function of a beam element equal to beta 1 plus beta 2 times x plus beta 3 times x squared plus beta 4 times x to the power 3, where I is the moment of inertia of a cross section, E is the elastic modulus, V or V of x is the lateral displacement, okay, and theta is the rotation. So V, we can call it, instead of lateral displacement, we call it vertical displacement, or maybe we leave it as lateral. Lateral means here not horizontal. Lateral means vertical to the member or perpendicular to the member. As you can see, our member is horizontal, so V1 and Vi and Vj are vertical. So lateral displacement means vertical or perpendicular to the elements. Theta is the rotation about z-axis. As you know, here we have x-axis, y-axis. So z-axis will be the axis perpendicular to the plane. Okay. Theta is the derivation of v by x. So the rotation is dv by dx. F is the shear force or the nodal force. M is the bending moment or the nodal moment. Again, moment about the axis. Okay, so this is generally the polynomial equation or the shape function for the lateral displacement of a beam element. And if we know V, the derivation of V according to X will be theta. Okay, for beam element, axial effect can be added. If we add the axial effect, it will be called a frame element. So the beam element and the frame element are very similar. So they can be added or neglected. If you are using only a beam element and excluding or neglecting the axial effect, so you don't need to include it. If it is a frame element, you have to include the axial effect. Okay. So if we go through all of this, we can go through later and let me know if you have any problem with it. But what we need to know is using same procedure. If we have the same procedure we have done in the bar element or truss element using shape function. Finally, we will get the case stiffness for the beam element. Again, what is the size of the stiffness matrix of a beam element? It is 4 by 4. So 1, 2, 3, 4, 1, 2, 3, 4. Why 4 element? 4 by 4 because we have 4 degrees of freedom. So 4 degrees of freedom give us a size of 4 by 4 for the stiffness matrix of a truss of a beam. Okay. What is the numbers inside? So we have 12 EI by L square, 6 EI by L, 12 EI by L to the power 3, 6 EI divided by L square. Here is negative 12 EI by L to the power 3, 6 EI to the power 2. If you notice here, so we have the first column is similar to the third column. But what is the difference between the first column and third column? The third column is the negative of first column. So 12, here negative 12. 6, negative 6. Negative 12, positive 6, positive 12, 6, -6. Okay, so you can notice that the third column will be the negative of the first column. For second row, we have 6ei by L squared, 4ei by L, say negative 6ei by L squared, 2ei by L. As you can notice here, we have 4ei by L, here 2ei by L. So this value is half of the value of this value in row in column 4 is the half of the value of column 2. Okay, and for row 3, what do you notice for row 3? Row 3 is a negative of row 1. So 12, -12, 6, -6, -12, 12, 6, -6. Okay. Row 4 is 6ei by L squared, 2ei by L, -6ei by L squared, 4ei by L. Again, this matrix can be can be driven from the shift function. Okay, but we need to focus on the value of it. I mean the parameter of it to use it in our example or our problem. Okay, but you need to notice some notice as I mentioned to make it easier for you to recognize if you need to recognize it. So the first column is same as third column but with negative sign. So if you know the first column, so the third column is the negative. Also, the first row and third row are similar, but the third row is the first row with a negative sign. Okay, another notice you need to know is if this is the diagonal is, do you know the diagonal line? So the numbers over the diagonal are similar to here. So this matrix is symmetric matrix. Symmetric matrix because the numbers over the diagonal is similar to the numbers below the diagonal. Okay. And another notice that this value is 4 and this value is half. So the value of the number in column 4, row 2 is half of the value in row 2, column 2. Okay, and the value in row 4, column 4 equal to double the value in row 2, row 4, column 2. Okay, so this is the general equation for beam member stiffness matrix. And the stresses in this member, sigma x. Sigma x is a normal stress or shear stress. Sigma is a normal stress. So the normal stress in a beam element equal to m times y divided by I. So if you want to get this moment using the equation on top, so we will use this formula. We will use this formula to get the moment. Okay. So after getting the stiffness matrix and get the values of B and D and using EI, so you can get the moment. Okay, and if you need the stress, you have sigma x equal to my by I. Okay, so now we don't need to do anything with this part now, but we just need to recognize K. So K for a beam element is 4 by 4 because we excluding the axial effect. If we include the axial effect, so the member will be called 2D beam element or frame element or beam element combining the axial effect or the axial stiffness. The first notice here, or what is the first notice we have here, or what is the first notice you notice? The first note is the element is 6 by 6. So if we include the axial axial effect in our calculation of the beam element will be 6 by 6, where it before was 4 by 4. So I just explain something to you here. Okay, so for 2D element, including axial effect. So this will be our element. The properties we know for this element will be E, A, and R. The length of this member is L. We have for this member node 1, node 2. What is the degrees of freedom we have here? We have 3 degrees of freedom. So we will have U1, V1, and rotation theta 1. So for your information, these are the positive signs for displacement. Displacement in X, displacement in Y, and rotation about Z or M. Okay, so we have three types of deformation. U is the displacement in X, V displacement in Y, theta is the rotation about Z, whereas Z is the axis perpendicular to this plane. So how many displacement we have here at node 2? Can you tell me? At node 2, we will have U2, V2, and theta 2. So how many degrees of freedom we have for this element? 4 or 6? 6. So why 6? What is added has been added to this element? So U2 and U1. So in this element, we add U1 and U2, which are the axial effect. That's why the degree of freedom becomes 6. And the stiffness matrix of this type of element will be 6 by 6. Okay? Do you have any problem with 6 by 6 element, where it come from? Okay, so now for beam element or frame element, K beam will become 6 by 6. I will write it down here with you. So we have 1, 2, 3, 4, 5, 6 times 1, 2, 3, 4, 5, 6. Okay, so we have 6 by 6 area. So if we write down from our last step, so we have here U1, V1, theta 1, U2, V2, theta 2. So the order of them, we start with the horizontal displacement, then the vertical displacement, then rotation. So horizontal displacement, vertical displacement, then rotation. Okay. What we have from last step for a beam element without axial effect, we have V1 theta 1, V2 theta 2, V1 V1, V1 theta 1, V2 theta 2. So I will start with this element first. So here we had in the last step 12 EI divided by L square, 6EI by L square, sorry, 12EI by L to the power 3, 6EI L square, and here negative EI by L to the power 3, 6EI L square. Okay, and for theta 1, this one was 6EI by L square, 4EI by L, here 2EI by L, and here is negative 6EI by L square. Okay, this one was the negative of rho 1. So these are the values of it. Okay, here similar to this one, 6EI by L square half 2EI by L, similar to negative 6EI by L square 4EI by L. Okay, so this is our the element from the previous element without the axial effect. For the axial effect, what is new in the axial effect? Here, the values here will be zeros because it is not existing. So what will be exist is just U1, 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 and U2, U2. So just the relation between U1, U2, U1, U2. So U1, V1 is not existing, so 0. Theta 1, U1 doesn't exist, so theta, so will be 0. Again here, V2, U1 doesn't exist, theta 2, U1 doesn't exist. Here as well, V1, U2 doesn't exist, theta 1, U2 doesn't exist, U2, U2 exists, V2, U2 doesn't exist, theta 2 doesn't exist. Here we have U1, V1 doesn't exist, U1, theta 1 doesn't exist, U1, V2 doesn't exist, U2, U1, theta 2 doesn't exist. So how many values we need to add? 1, 2, 3, 4. Here as well, this 0, 0, 0, 0. Okay, how much is the values here? The values here is the axial stiffness from the truss element. This is the axial stiffness effect. So just keeping in mind, from the bar element, this is called axial effect because the bar element was only including the axial effect. So the axial effect here is EA by L. So if we add this here, so this EA by L, this negative EA by L, because if you remember again, the truss element was positive, negative, here negative EA by L, here positive EA by L. So this is our final matrix or final stiffness matrix for the truss for the frame element, including the axial effect. Do you have any question for this one? Do you understand what is the difference between this one and the previous one? Okay, so the axial effect makes the stiffness matrix 6 by 6 instead of 4 by 4, and the axial stiffness was added EA by L. Okay, so now I will turn back to the screen. So this is our final stiffness matrix for a frame element. I hope you can understand the difference between both of them. And now, this is just a reminder of the boundary conditions. So the boundary conditions, we need to know that the boundary conditions are in order to prevent the finite element model from moving freely through the space. Each of the possible degree of freedom must be concentrated somewhere on the model. As you know, any structure needs to be restrained from movement at least in one direction. Otherwise, if you don't add any boundary condition or any support, the structure will be moving in the space, like flying or moving. So we are dealing with static structure for this part of the course. So you need to add degrees of freedom. The degrees, sorry, the the boundary condition. The boundary condition like the fixed support or hinged support or ruler support. Okay. So as the roller support prevents the movement in one direction, so it has one reaction. Okay, and also hinged support prevents the movement in two directions, x and y, so it has two reactions. The fixed support prevents the movement in x direction, y direction, and rotation, so we have three reactions. Okay. In general, the displacement boundary conditions simulate the actual support of the structure. Same as general structure analysis, there are three basic types of support: simply supported, fixed, and roller support. Okay, I will share with you again something. Okay, so the boundary conditions we have is any that we need to know that any node, if you just leave it without any boundary condition, it is a free node. For the 2D beam element, how many degrees of freedom we have at each node? 3. So we have, do you want me to wait until you finish? Or it's all good? Okay. Now, for the boundary condition again, we have for 2D beam element, because we was talking about 2D beam element. The basic things we have is the free node. If we have a free node in black, so this is a free node. How many degrees of freedom at free node? We have 3 degrees of freedom at a free node. U, V, and theta. So each free node has 3 degrees of freedom in 2D beam element. This is the general thing. For boundary conditions mean restriction of movement. What type of boundary conditions we have? First is the ruler support. If we have a ruler support, what you know about ruler support? The ruler support will have 3 degrees of freedom as well, U, V, and theta, because this is a node. But because it is supported by a ruler, so the value of V will equal to 0. So this is the boundary condition here. So What you understand from this? We understand that from this support, the value of v becomes 0. So it is not unknown now. It is known for us. So how many unknowns we have at this node? Only two, u and theta. If we apply same thing on the hinged support, the hinged support is quite similar to the roller support. It also has, it is a node, so it has 3 degrees of freedom, u, v, and theta. What are zeros here? The boundary condition here is a hinge. So hinge is preventing the vertical movement, so v will be 0. Also preventing the horizontal movement, so u will be 0. So how many unknowns we have here? Only one, which is theta. The third type of supports we have is fixed support. If we have a fixed support like this, so this is our node. How many unknowns or how many degrees of freedom we have at this node? 3. Again, u, and this one is v. And this is theta. The fixed support prevent the vertical movement, so u will be 0. Sorry, v will be 0. And horizontal displacement, so u will be 0. And also prevent rotation, so theta will be 0. So how many unknowns here, or how many degrees of freedom we have here? None. So all are known here. Here we just need to know theta. Here we need to know theta and u. Okay, so this is what is meant by boundary condition. The boundary condition will affect our degrees of freedom because the boundary condition will give us information about the displacement. So some of displacement will be known due to the boundary condition. Okay. So the application of boundary condition depends on the type of structure being analyzed, also on the finite element program being used. So as you see, my boundary condition in the previous explanation was depending on a 2D beam element, including the axial effect. But if it is 2D beam element excluding the axial effect, it will be different because the degrees of freedom will be only 2. So the boundary condition depends on the type of element or type of structure. Also, the program supports if the program supports 2D elements, the application of boundary condition in the third dimension is unnecessary. This is what I was talking about. If you are doing a 2D beam element, so we can just add the displacement or the movement u, v, theta. But if we are in 3D, more axes will be added. So we will have z-axis as well. So we need to add the displacement in z-axis. So this means that in 3D elements, the degrees of freedom or the boundary condition are different from 2D. So we need to know if the problem is 2D or 3D. On the other hand, program using 3D elements for 2D problems require all displacement in the third dimension are 0. So there is also a note you need to keep in mind that some softwares are dealing with only 3D elements, so they cannot deal with 2D elements. So you need, in this case, you need to add all if you are in a 2D problem, you need to like put all the boundary condition and supports as 0 in the third dimension or in 3 dimension. Okay. The last thing we need to know about boundary condition that engineering judgment or assessment of the boundary condition need to be done because the boundary condition needs to simulate closely the behavior of structure. So in some cases, we need to know that we need to like run the model or model the structure with different boundary conditions to get the best simulation of the structure. Because in some cases, the real support is hinge, but when you model it as hinge on the software, it doesn't give you accurate behavior of the structure. So maybe you need to change the support or remodel it using a different boundary condition. Okay, so the boundary condition is important thing we need to know in the model because it will affect the 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 behavior, and we need to take this into consideration. Okay. Do you have any questions about this stuff? So now we know how to derive the bar element stiffness matrix using the direct method and the the formal procedure or the shape function. And also we know how to use the shape function to get the beam element stiffness matrix, which is not very important to focus on. But we need to know what is the stiffness matrix for the truss element and the beam element. And if we include the axial effect in the beam element, what is the difference and what is the stiffness matrix looks like? Then now we will go to the step I delayed, which is the example. So can you see my screen now? We have an example of a bar element. We need to find the stresses in the two bar assembly, which is loaded with force B and constrained and to end as shown in figure. Okay, can you see it? I will explain this example with you. Just a second. So for this bar, as you can see, the bar element has a shape. We have two different shapes, or there is a differentiation in shape at the middle, so we cannot model it as one element. So this element, this problem, because the shape is changed through the elements, so we need to model it in two parts. Okay. Now I will just share painting, share paint with you. So if we have a problem, so this is our axis. Okay. So this is our element. As you know, it is a bar element or two bar element. It is given to us that the length of the two member is equal L L. But this member, member number one, this number two, this member has two A and E, and this one has A and E. So the value of E is similar, so they are from same material, but the area of this one is double area of this one. That's why it's 2A and A. And we have one force here equal to B. And given to us, this is node 1, node 2, and node 3. This is x-axis and y-axis. Okay? What we need to do here, we need to find traces in member 1 and member 2. This is the requirement. Okay, first of all, I will remind you with what is the stiffness matrix of a truss. Okay, equal to EI, EA by L, 1, -1, -1, 1. So this just to keep in mind, stiffness matrix of a bar element or a truss element. How can we start this? First of all, we know that it is a truss, so it will be the members will be under tension or compression force. So it will be elongated or shrink, or it may mean compressed or pulled. So what we need to know firstly is to construct stiffness matrix for each member. So we have K1 and K2. Then using K1 and K2, we will construct the global matrix or overall stiffness matrix. How can we construct the stiffness matrix for this one? For member one. For member one, you just substitute here. E is E and times 2A divided by L times 1, -1, -1, 1. So this is equation number one. So K1 equal to 2EA divided by L, 1, -1, -1, 1. As you know, here, this is 2 by 2. If we can you tell me 2 by 2, how it is 2 by 2? So if we look here, this is our member number 1. Start with equation 1, node 1, node 2. How many degrees of freedom we have for this truss? We have here U1 and here U2. Okay. For member 2, we have node 2, node 3. We have U2 and U3. So the stiffness matrix for this member is 2 by 2. For this member is 2 by 2 because we have 2 degrees of freedom, 2 degrees of freedom. So now we construct the stiffness matrix for member 1. For member 2, K2, what is the difference between K1 and K2? K2 will be similar to K1. Instead of A was 2A in member 1, it will be A in member 2. So member 2, EA divided by L, 1, -1, -1, 1. Okay. This is the stiffness matrix for each member. Second step is the global matrix. Just increase the page size. How can we construct the global stiffness matrix here? So second step will be global stiffness matrix. The first thing we need to know that K global for this member, how many degrees of freedom we have total for this member, for this structure. We have U1, U2, and U3. So the total number of degrees of freedom here is 3. U1, U2, U3. So the K global for this structure will be 3 by 3. So if I do it here, so we will have 1, 2, 3, 1, 2, 3. Can anyone help me to do this one? There is an easier way to do it. So we'll try to do it. Or first of all, here, this U1, U2, U3, U1, U2, U3. Here, U1, U2, U1, U2. Here, U2, U3, U1, U, sorry, U2, U3. What we need to do is combining the stiffness matrix of member 1 and 2 together and put it here in the K global matrix. What we need to do is just add U1, U1 together and put it here. How many U1 we have? Just make different colors. So first of all, this is U1. Do we have any U1 1 member? This is U1 1. So just one here. Or we have any other thing here? Sorry, this two. So I will just adjust this one here, just to take two inside to make it easier. So what we need to do here is just because K global has a common factor of EA by L, so I will take it outside here, EA by L as a common factor here, and we will have two. So just edit this one, remove the two from here, and take it inside. So this will be 2, -2, -2, and 2, just to make it easier when we calculate. So how many U11 we have? Only member 1, 2, which is equal to 2. So I have one member, the value is 2. For U21, do we have any U21? Here we have only this one in orange. We don't have in this matrix any U21. So U21 here will be -2. For this one, U31, do we have any relation between 3 and 1? We don't have here. We have U11, U21, U12, U22. Here U22, U32, U23, U33. So we don't have any U31 member, so this will be 0. Okay. For second row, we have U2. So here U1 with U2. U1 with U2, we have this member only, so it will be -2. For U22, we have a common thing here. This first thing we have 2 and we have 1 here. So U22, we have 1 from first matrix, 1 from second matrix. So we some add them together. So we have 3. Okay. The next step is U32. U32, we don't have any 3 in the matrix 1, so we have U32 is this number, -1. So next one we have U13. U13, we don't have any U13, so it will be 0. Next we have U23. U23 is only here, so it will be -1. The last one will be U33 only here, so it will be 1. So if you have a look on the matrix, the common thing is only this number or this value, which is U22, because we have node 2 here and node 2 here. So this is how to construct the stiffness matrix or global stiffness matrix, is to just take the values common together and add them together to construct the stiffness matrix for the whole structure. Okay, so after we finish this step, the first step, we know that K global is EI divided by L times -2, -2, 0, -2, 3, -1, 0, -1, 1. Okay, this is called the global stiffness matrix. There is a thing we need to know here that this is the diagonal member I was talking about before. This is called diagonal member or diagonal row or the diagonal, only the diagonal. This is the diagonal row. What you notice for the matrix, what you notice above the diagonal, this part is symmetric with the bottom part. So if this is our diagonal, so the bottom part is symmetric with the top part. So if this 0, this 0. This -1, this -1. This -1, this -1. So when we construct the global matrix, you can benefit from this, that we need to calculate the diagonal and the top part or the bottom part because it is symmetric. Okay, so now we finalize the first step and get the global stiffness matrix. What else? We need to get the displacement, the nodal displacement. The general equation for the nodal displacement is the force F equal to K global times D. This is our general equation. Now we already have K global. So we need to know what is the load vector and what is the displacement vector. What is the force vector or the load vector? How many nodes we have? We have 1, 2, 3 nodes. This is member 1, this is member 2. So we have force at node 1, F1, force at node 2, F2, force at node 3, F3. Okay, so the force, the load vector, F, will be F1, F2, F3. What we know from this? Do we have any applied load? If you return back to the problem, what you will find? We'll find that this is our problem, and this is node 2. What we have at node 2, if you have a look, we have at node 2 a force B. So we need to replace F2 by positive B. Why positive? Because this is our sign convention, X, Y, and moment. So the final force, do we know the force F? The force F1 is unknown for us because it is a reaction. The force F2 here, F3 here is also unknown. So F1 and F3 are unknowns because they are reactions, but F2 is known because we have applied load there. So we can say that the load vector is F1, B, and F3. F1 and F3 are unknowns because they are reactions. For the nodal displacement, D. D, how many displacement we have? U1, U2, U3, right? So the nodal displacement, U1, U2, U3. Do we know anything about the nodal displacement? So this is the displacement vector. We need to apply the boundary condition here. Can anyone apply the boundary condition? What is the boundary conditions we have here? We have here support and here support. This support is a fixed support, but for a truss, what this support will do? This support will prevent the displacement at node 1 and prevent the displacement at node 3. So U1 will be 0, U3 will be 0. So the displacement can be written as D equal to 0, U2, and 0. And the final force vector or load vector is F1 plus B F3. So now we know F and D. Do you understand from where I get 0 for U1 and U3? Because U1, you have support here, so there is no U. Here, we have also support here, so U3 will be 0. Now, the last step is after we get all this, so we apply in the equation we have F is equal to K times D. So if we have F1, B, and F3. For K, we have EA by L, 2, negative 2, negative 2, 3, 0, negative 1, 0, negative 1, 2. Oh, sorry, 1. Okay. This times the displacement vector, which is 0, U2, 0. So, is there any problem with this? This is the force vector. This is the K global vector. This is the displacement vector. So what is the unknowns we have here? Only U2. So from this equation, we get U2. How can we do this multiplication? This one is very easy because we have 0 and 0. So to do this, you can just, if you multiply, you know how to multiply. Can first we multiply this two matrix or this matrix and vector? The first matrix is 3 by 3. Second vector is 3 by 1 because we start row times column. So we have 3 rows and 3 columns. Here we have 3 rows, 1 column. Okay, can we multiply this together? To multiply both together, we need to make sure that these are same value or same number. So 3 and 3. So now we can multiply them together. And the product will be 3 by 1. So the product is 3 by 1 because this one is 3 by 3 and this one is 3 by 1. Okay. So for our calculation, if we do this, F1 positive B, F3 will be EA divided by L times. If I multiply, how we can multiply? We multiply first row with the first column. So it will be, just I will do it only for the first one. Just to remind you. So for the first row, we have 2 times 0 minus 2 U2 plus 0. Okay. Second one, we have negative 2 times 0 because we are multiplying row 2 times column 1. So this one will be plus 3 U2 minus 1 times 0. The third one will be row times column. So 0 minus U2 plus 1 times 0. So the final will be EA by L times this one negative 2U2 plus U3U2 and here negative U2. Okay. So we need to get which equation can give us U2, the value of U2. The only equation to give us the value of U2 is the second equation. So plus B will be equal to EA divided by L times 3U2. So U2 will be equal to BL divided by 3EA. So this is the value of the deformation U2BL divided by 3EA. Okay, so we get the displacement at 2, at node 2, or deformation at node 2 equal to B positive BL divided by 3A. Positive EL, positive means to the right. Okay. Do you have any problem with the displacement? This is the main thing we need to know is the nodal displacement at 2. But this is not the requirement. But this is the main thing to get the requirement. So the requirement is to find the stress sigma 1 and sigma 2. So sigma 1, stress in member 1. If you return back to the shape function equations, we will find that E times epsilon is the stress, where epsilon is B1 times U1, the displacement. So the final formula, E times B1 times U1 is the stress, where B1 is E, sorry, B1 is negative 1 divided by L, 1 by L. This is a vector of B. If you return back to the slide, just show you this part. Can you see the screen now? What is B? B is the element, the strain displacement matrix. Okay, so if we return back to our calculation again. So this is B. Okay, U1 is the deformation for member 1, so it is U2 and U1 and U2. So the equation of stress here can be written as sigma 1 equal to E times negative 1L, 1L times U1, U2. Okay, we know that from the previous slide calculation, U1 is 0, and we get U2 as BL divided by 3EA. So sigma 1 will be E. This one is 1 row times 1 column, so it will be negative 1 divided by L times 0 plus 1 by L times BL by 3EA. So this is 0, so it will be E, and we will get L by L, so E, B divided by 3AA. Again, E with E, so it will be B divided by 3A, positive. So the stress in number 1 will be positive B divided by 3A. The positive sign means this is tensile stress. So member 1 is under tension. Okay. So this is what we get from member 1 calculation. Now we get to member 2. For member 2, Sigma 2, what is the difference between sigma 1 and sigma 2? Sigma 2 will be, the general equation is E epsilon 2 will be E B2 U2, the displacement of member 2. So sigma 2 will be E times negative 1 by L, 1 by L, times what is the displacement of member 2? Displacement of member 2 are U2 and U3. So we have U2 and U3. Okay. So from our previous calculation, we get U2 as BL by 3A EA, U3 as 0. So sigma 2 will be E negative 1L positive 1L times BL by 3EA and 0. So we again multiplying row by column. So it will be E negative 1 by L times BL 3EA plus 0. So if we omit E with E, L with L, what we will get is the stress at member 2 will be negative B by 3EA. So similar procedure as member 1, so it becomes negative 3EA. What is meant by negative? Negative means comparative stress. Okay, so this means that member 2 is under compression. Okay, so member 2 is under compression, member 1 is under tension. If we return back to the slides, it's our last thing I will say. Okay, if we return to the example, if you have a look on the example, what you can note from the example that point 2 has a force B. From our first look, we will see that member 1 is under tension because B is pulling member 1. Member 2 will be under compression because the force B is pushing node 2. So our calculation are logic because member 1 is under tension and member 2 is under compression. Okay, so this is just a check of what we are doing is correct, and hopefully you understand what I have explained in this example. Do you have any question for this one? Do you have any question? Okay. I just have a question for you. Is there anything, any way that we can contact together? I already have the recording of the last session and this session, but I don't know how to send it through to you. Is there any group or any forum or anything that we can contact together? Okay, I can send the link to the Professor Keizing, and maybe he can forward it to you. Is that okay?
他这个和咱们这个全联系，他有微信吗？